Imagine a cosmic ballet so intricate, so densely packed with stellar performers, that it defies everything we thought we knew about how stars are born and behave. We are not talking about binary systems or even triple star systems. Today, we are plunging into the mind-bending realm of UNDECUPLE star systems, celestial conglomerates where 11 stars dance in a gravitational embrace. These aren't just rare, they are cosmic enigmas challenging our fundamental understanding of stellar formation and dynamics. Over the next few minutes, prepare to have your perception of the universe twisted and expanded as we explore 25 strange discoveries about these UNDECUPLE star systems. From unstable orbits and chemical composition variations to age discrepancies and the surprising presence of circumstellar disks, each discovery unveils a layer of complexity that deepens the mystery. We will journey through X-ray emission anomalies, the alignment of stellar spins, and even speculate on the potential role of dark matter in these systems. Get ready to explore how these systems disrupt protoplanetary disks, challenge our understanding of metallicity variations, and offer rare eclipsing events that provide crucial data. These systems lead to stellar ejections, create unique conditions, and could even be sources of gravitational waves. This exploration promises not just to inform, but to ignite a sense of awe and wonder at the sheer complexity and beauty of our universe. So buckle up, because first, we need to talk about the unstable orbits of UNDECUPLE stars. The first discovery involves the inherently unstable orbits within UNDECUPLE star systems, and it stems from the gravitational interactions in such a crowded environment, leading to orbits that are anything but predictable. With 11 stars packed relatively closely together, the gravitational forces at play are incredibly complex. Each star constantly tugs on all the others, creating a chaotic dance where predicting long-term stability becomes a monumental challenge. Unlike our solar system, where planets orbit a single, dominant star in a relatively orderly fashion, these systems are characterized by constant perturbations and shifts. To understand these complex movements, scientists rely heavily on sophisticated simulations and models. These models take into account the mass, velocity, and position of each star, then use the laws of gravity to calculate how they will interact over time. However, even with the most powerful supercomputers, accurately predicting the future of these systems is incredibly difficult. The slightest change in initial conditions can lead to drastically different outcomes, a phenomenon known as the butterfly effect. This makes it nearly impossible to know exactly where each star will be millions or billions of years from now. Moreover, these simulations often need to simplify certain aspects of stellar physics to make the calculations manageable, introducing further uncertainties. Despite these challenges, these simulations provide invaluable insights into the dynamics of UNDECUPLE star systems. They help us understand how stars can maintain some semblance of stability, what types of orbital arrangements are more likely to last, and what factors might lead to the ejection of stars from the system. These models also allow us to test different theories about star formation and evolution, providing crucial clues about the origins of these fascinating celestial arrangements. With those simulations in consideration, the next point is that we should dive into the chemical composition variations within these systems. Exploring the chemical composition variations, one of the most puzzling aspects of UNDECUPLE star systems is the unexpected differences in the elemental makeup of stars within the same system. According to standard stellar formation theories, stars born from the same molecular cloud should have very similar compositions. Yet, observations of UNDECUPLE systems often reveal significant discrepancies in the abundance of elements like iron, carbon, and oxygen among member stars. One theory to explain these chemical differences involves accretion from different nebular materials. In the chaotic environment of a star-forming region, the gas and dust cloud from which stars are born isn't perfectly homogeneous. Different regions of the cloud might be enriched with material from nearby supernova or have varying densities of certain elements. As stars form, they accrete material from their immediate surroundings, leading to differing compositions depending on their location within the cloud. Another potential cause is tidal stripping, a process where the gravitational interactions between stars can alter their surfaces. In close binary or multiple star systems, the gravitational pull of one star can strip away the outer layers of its companion, exposing deeper layers with a different chemical makeup. This process can be particularly effective in undercouple systems, where the close proximity of stars increases the likelihood of tidal interactions. Spectroscopic data visualizations play a crucial role in understanding these chemical variations. By analyzing the light emitted by each star, astronomers can determine the abundance of different elements in their atmospheres. These spectra act like fingerprints, revealing the unique chemical signature of each star and allowing scientists to identify any anomalies. These spectroscopic analyses often reveal that some stars are enriched in heavier elements while others are deficient, pointing to complex formation and interaction histories. As we consider these potential alterations to chemicals, we must delve into the age discrepancies within systems. Turning our attention to a different puzzle, the age discrepancies within systems present another challenge to our understanding of undercouple star formations. According to standard stellar formation models, stars within the same system should be roughly the same age, as they are believed to form from the same molecular cloud at roughly the same time. However, observations of undercouple systems often reveal that stars in the same system can have significantly different ages, sometimes differing by millions or even billions of years. This age disparity defies conventional wisdom and raises intriguing questions about the formation and evolution of these complex systems. One possible explanation for these age discrepancies is stellar mergers. In the crowded environment of an undercouple system, stellar collisions and mergers are more likely to occur. If two stars merge, the resulting star would be younger than some of its companions, as its formation would have effectively reset the clock. The merger could also alter its chemical composition, further complicating the picture. Such mergers could be triggered by gravitational interactions within the system, destabilizing orbits and leading to direct collisions. Another explanation involves capture events. Undercouple systems might not always form as a single entity. Instead, they could assemble over time through the gravitational capture of unrelated stars. A star that formed elsewhere could wander into the gravitational influence of a forming or already established multiple star system and become bound to it. If the captured star originated from a different star-forming region or formed at a different time, it would naturally have a different age than the original members of the system. Diagrams illustrating these scenarios can help visualize these complex processes, and these diagrams often depict the chaotic interactions within the system, showing stars merging or being captured, which adds to the visual understanding of these scenarios. Given these insights, we now must examine the presence of circumstellar disks. Diving into another fascinating aspect, the presence of circumstellar disks around stars in undercouple systems presents a real surprise because these disks are composed of gas and dust, and they are the birthplaces of planets. In a multiple star system, especially one as crowded as an undercouple system, the gravitational forces are expected to be chaotic and disruptive. These forces should quickly disperse any circumstellar disks, preventing planets from forming. Yet, observations have revealed that some stars in these systems do indeed possess stable circumstellar disks, which challenges this expectation and leads to many new questions. The existence of these disks suggests that planet formation is possible even in these extreme environments. This discovery has significant implications for our understanding of planetary formation, hinting that planets might be more common in multiple star systems than previously thought. The gravitational dynamics in an undercoupled system would likely make planet formation quite different from that around single stars. Rather than forming in neat circular orbits, planets in these systems might follow more eccentric paths, experiencing dramatic variations in temperature and light as they orbit their host stars. The gravitational interactions could also lead to the ejection of planets from the system or even collisions between them. The survival of circumstellar disks in undercoupled systems also provides clues about the conditions needed for planet formation. Perhaps these disks are particularly massive, allowing them to withstand the disruptive forces, or maybe the stars have settled into an arrangement that minimizes gravitational disturbances. Artist renditions of potential planetary systems in undercoupled systems often depict planets orbiting stars amidst a dazzling array of stellar companions. These planets may appear exotic, with unusual climates and appearances shaped by the complex lighting and gravitational environment. However, the presence of such disks raises the exciting possibility that planets could form and persist even in these dynamically complex environments. Now, let's shift our focus to unusual light curve patterns observed in these systems, turning our attention to another mystery. Some stars in undercoupled systems exhibit perplexing light variations that defy standard explanations. These light patterns, which astronomers call light curves, track how the brightness of a star changes over time. In many binary or variable star systems, these curves follow predictable patterns. For instance, eclipsing binary stars show regular dips in brightness as one star passes in front of the other. Variable stars, on the other hand, pulse with a consistent rhythm, their brightness fluctuating due to internal processes. However, the light curves of some stars in undercoupled systems are anything but typical. They show erratic, unpredictable changes in brightness that do not align with any known models for binary or variable stars. These unusual patterns suggest that something complex and unseen is at play, something that goes beyond the usual stellar interactions. One possible explanation for these strange light curves is the presence of unseen companions. Even in a system with 10 stars, there could be smaller, dimmer objects like brown dwarfs or even planets orbiting a star. If these unseen companions pass in front of the star, they could cause irregular eclipses that disrupt the light curve. Imagine a star with several small objects orbiting it at different angles and speeds. The resulting eclipse pattern would be complex and difficult to decipher. Another potential cause is complex magnetic activity. Stars can have strong magnetic fields that generate star spots, similar to sunspots on our sun. These star spots can affect a star's brightness, and if a star has a particularly complex magnetic field, it could produce unusual light curve patterns. The magnetic fields of stars in undercoupled systems may be influenced by the gravitational forces of their many companions, leading to highly irregular activity. These magnetic fields could lead to powerful stellar flares. To illustrate these patterns, light curve graphs of these stars often show a series of peaks and dips that appear almost random. Unlike the smooth, predictable curves of typical variable stars, these graphs are jagged and chaotic. Analyzing these light curves requires sophisticated techniques and powerful computers to try and tease out any underlying patterns. Astronomers use these observations to develop new models that can account for the complex interactions within these systems, piecing together the puzzle of these stellar enigmas one observation at a time. These efforts may eventually reveal the hidden dynamics of these crowded star systems and challenge existing models of stellar behavior. This raises questions about the high stellar density within these systems, which is our next point of discussion. Now, let's consider the puzzle of high stellar density. Undercoupled star systems pack a remarkable number of stars into a relatively small space. The stars in the core of these systems are often incredibly close to each other, much closer than what standard models of stellar dynamics would predict as stable. According to these models, such close proximity should lead to frequent collisions or ejections of stars from the system. The fact that these systems exist at all suggests that there are mechanisms at play that we do not fully understand. One potential mechanism that could prevent stellar collisions is hierarchical arrangements. In a hierarchical system, the stars are organized into multiple levels of orbits. For example, two stars might form a close binary pair, and then that pair orbits another star at a greater distance. This arrangement can repeat itself with pairs of stars orbiting other pairs, forming a complex, multi-layered system. The hierarchical structure helps to stabilize the system by distributing the gravitational forces and preventing any one star from getting too close to another for too long. Simulations show that hierarchical systems can remain stable for billions of years, even with a high density of stars. Another stabilizing factor could be strong magnetic fields. Stars have magnetic fields, and when stars get very close to each other, their magnetic fields can interact. These interactions can create forces that counteract the gravitational forces, preventing the stars from colliding. This is still a fairly new area of research, and the details of how magnetic fields might stabilize undercuple systems are not yet fully understood. Computer models show that strong magnetic fields can significantly alter the dynamics of these systems, but more observations are needed to confirm these effects. Comparative visualizations of simulated star systems, some with hierarchical structures and others without, clearly show the increased stability afforded by these arrangements. In simulations of non-hierarchical systems, stars tend to scatter and collide relatively quickly. In contrast, hierarchical systems maintain their structure and stability over much longer periods. These visualizations are crucial for understanding the long-term dynamics of undercuple star systems and how they manage to defy our initial expectations. But why don't we see more massive stars in these systems, which leads us to our next exploration? Let's now turn our attention to a curious observation: the lack of massive stars in many undercuple systems. Massive stars, those giants that burn brightly and live fast, are surprisingly rare in these complex stellar arrangements. This dearth presents a puzzle when we consider that star formation regions typically birth a range of stellar sizes, including some truly enormous stars. The prevailing theory suggests that the disruptive environment within undercuple systems hinders the formation or survival of massive stars. The gravitational forces exerted by numerous companions can interfere with the accretion process, preventing stars from gathering enough material to reach a massive size. Imagine a star trying to grow but constantly being tugged on by multiple gravitational forces. It is like trying to build a sandcastle while someone keeps knocking it down. This constant disruption makes it difficult for any single star to dominate and accumulate the mass needed to become a true heavyweight. In contrast, consider star formation regions that give rise to massive stars. These regions often feature large, relatively isolated clouds of gas and dust, allowing individual stars to grow without significant interference from nearby companions. The absence of such isolation in undercuple systems creates a bottleneck, limiting the maximum size that any star can achieve. Stellar size comparison charts vividly illustrate this point. While typical star-forming regions boast a spectrum of stellar sizes, including some that dwarf our Sun, undercuple systems tend to cluster towards the lower end of the scale, with smaller, less massive stars predominating. This difference poses significant questions about star formation processes and the conditions necessary for massive stars to emerge. Are there specific scenarios within undercuple systems that could potentially allow for the formation of massive stars? Or is their absence a fundamental characteristic of these crowded environments? The answers to these questions could reveal important insights into the interplay between gravity, stellar dynamics, and the ultimate fate of stars in multiple star systems. But what happens when a star leaves the undercuple star system? Transitioning from the puzzle of missing massive stars, we now consider an equally dramatic phenomenon: the ejection of stars from undercuple systems. Evidence suggests that the intense gravitational interactions within these crowded environments can sometimes lead to stars being flung out, becoming stellar orphans adrift in the vastness of space. These ejections are not mere theoretical possibilities. Astronomers have observed stars with trajectories and velocities indicating that they were likely ejected from a multiple star system. The dynamics of these ejections are complex, governed by the intricate dance of gravity between numerous stars. When stars pass too close to each other, their gravitational forces can become a slingshot, accelerating one star to immense speeds while altering the orbits of the others. If a star gains enough velocity, it can escape the gravitational pull of the entire system, embarking on a solitary journey through the galaxy. Simulations of these interactions reveal the chaotic nature of stellar ejections, with stars often following unpredictable paths before being expelled. The impact of these ejections on the remaining system can be significant. The loss of a star alters the gravitational balance, potentially leading to further instability or even the eventual disintegration of the entire system. Imagine a carefully balanced mobile where removing one weight causes the whole structure to shift and wobble. Similarly, the ejection of a star can trigger a cascade of orbital adjustments, affecting the long-term stability of the remaining stars. Animations of stellar ejections vividly illustrate this process, showing how the expulsion of one star can send ripples of change throughout the system. These stellar orphans, now free from their companions, offer a unique opportunity to study stars in isolation. By analyzing their properties, such as their age, composition, and velocity, astronomers can piece together clues about their origin and the conditions within the UNDECUPLE system they once called home. Understanding these ejections provides valuable insights into the dynamic processes that shape the evolution of multiple star systems and the distribution of stars throughout the galaxy. But how do these stars emit strange signals across the galaxy? Turning our attention to another cosmic enigma, we find unexpected levels of X-ray radiation emanating from certain stars within these UNDECUPLE systems. Standard models of stellar activity struggle to account for these anomalies, presenting a puzzle that astronomers are actively working to solve. These X-ray emissions are not just slightly elevated, they often exceed what would be expected based on the star's age, mass, and surface temperature. The source of this excess X-ray radiation is believed to be linked to enhanced magnetic activity. In single stars, magnetic fields are generated by the movement of plasma within the star's interior, a process known as the dynamo effect. These magnetic fields can erupt on the surface, creating flares and other energetic phenomena that emit X-rays. However, in UNDECUPLE systems, the gravitational interactions between stars can amplify these magnetic fields, leading to more frequent and more powerful flares. Another potential source of X-ray emission is accretion. If a star is pulling material from a nearby companion, this material can form a disk around the star before eventually falling onto its surface. As the material spirals inward, it heats up to millions of degrees, emitting intense X-rays. This process is common in binary systems, but it can also occur in UNDECUPLE systems where stars are in close proximity. The increased amount of gravitational forces in these systems further contributes to the heating of the gases to extreme values. The observation of these X-ray anomalies challenges our understanding of stellar activity in multiple star systems. It suggests that the presence of numerous companions can fundamentally alter the processes that govern a star's magnetic field and its interaction with its environment. This requires refining our theoretical models to account for the complex interplay of gravity, magnetism, and accretion in these extreme environments. With these strange X-ray signals identified, the alignment of the stars themselves comes next. Transitioning from the realm of intense energy emissions, we now turn to a more subtle but equally intriguing phenomenon, the alignment of stellar spins. In many UNDECUPLE star systems, astronomers have observed a surprising degree of alignment in the rotational axes of the stars. This means that the stars are all spinning in roughly the same direction, as if they were coordinated by some unseen force. This alignment is unexpected because undercuple star systems are inherently chaotic environments. The gravitational interactions between so many stars should, over time, scramble their orientations. The fact that we see alignment suggests that there must be a mechanism at play that counteracts these disruptive forces. One theory is that the stars formed from a single, large molecular cloud that was already rotating in a particular direction. As the cloud fragmented and collapsed to form individual stars, they inherited the original rotation of the cloud. This would naturally lead to an alignment of their spin axes. However, maintaining this alignment over billions of years is a challenge. Gravitational perturbations from other stars in the system can gradually alter the spin axes, causing them to drift out of alignment. To explain the observed alignment, some researchers propose that tidal forces may play a role. Tidal forces arise from the gravitational pull of one star on another and can act to synchronize their rotations. While tidal forces are typically thought to be most effective in close binary systems, they may also have a subtle but significant effect in undercuple systems, helping to maintain the alignment of stellar spins. Another possibility is that magnetic fields could be involved. If the stars in the system have strong magnetic fields, these fields can interact with each other, creating torques that tend to align the spin axes. This mechanism is similar to how magnetic fields can align the spins of planets in our solar system. It is important to note that the alignment is usually not perfect. There is always some degree of misalignment, which can provide clues about the age of the system and the strength of the disruptive forces at play. The discovery of aligned stellar spins in undercuple systems provides valuable insights into the formation and evolution of these complex systems. It suggests that these systems may have formed in a more ordered fashion than previously thought, and that there are mechanisms at work that help to maintain their structure despite the chaotic gravitational environment. Having observed their spins match up, the disturbances they cause on any planets that may try to form comes next. Turning our attention to the prospects of planet formation, the gravitational forces in undercuple star systems can severely disrupt protoplanetary disks, hindering planet formation. These disks, which are swirling clouds of gas and dust around young stars, are the birthplaces of planets. However, in the complex gravitational environment of an undercuple system, these disks can be torn apart and warped, making it difficult for planets to form. Computer simulations have provided valuable insights into the effects of these disruptions. These simulations show that the gravitational forces from multiple stars can create spiral arms, gaps, and warps in the protoplanetary disks. These features can disrupt the orderly process of planet formation, preventing dust grains from clumping together to form larger bodies. In some cases, the disks can be completely dispersed, leaving no material for planets to form at all. The severity of the disruption depends on several factors, including the masses and orbits of the stars in the system, as well as the size and density of the protoplanetary disk. Systems with more massive stars in close orbits tend to be more disruptive, while larger and denser disks are more resistant to disruption. The simulations also reveal that the location of the disk within the system is important. Disks that are located closer to the stars are more likely to be disrupted than those that are farther away. Visualizations of these disk disruption scenarios are quite striking. They show the protoplanetary disks being stretched, twisted, and torn apart by the gravitational forces of the stars. These images provide a stark reminder of the challenges that planets face in forming in such extreme environments. Despite these challenges, some simulations have shown that it may still be possible for planets to form in certain regions of undercuple systems. For example, planets may be able to form in stable orbits around individual stars or in circumbinary orbits around a pair of stars. However, these planets are likely to have very different characteristics than the planets in our solar system. The disruption of protoplanetary disks is a significant obstacle to planet formation in undercuple star systems, yet there could be other implications for the development of those systems which we will now consider. Let's now turn our attention to one of the most perplexing questions about undercuple star systems, the formation paradox. The very existence of these systems challenges our understanding of how stars come into being. How can such a complex, tightly packed group of stars form in the first place, given the inherent chaos of star formation regions? One prevailing theory suggests that undercuple systems arise from the fragmentation of large molecular clouds. These clouds, vast reservoirs of gas and dust, are the birthplaces of stars. According to this theory, a massive molecular cloud can collapse under its own gravity, fragmenting into smaller clumps. If the conditions are just right, these clumps can further fragment, eventually leading to the formation of multiple stars, potentially up to undercuple. However, the challenge lies in explaining how these fragments can remain bound together in a stable system, rather than drifting apart or merging into a smaller number of stars. Animated formation models of this theory display a complex interplay of gravitational forces, gas dynamics, and radiative feedback. The initial cloud begins to contract, forming dense cores that subsequently collapse and fragment. These fragments then condense into protostars, which continue to accrete material from the surrounding cloud. Another competing theory proposes that undercuple systems form through sequential capture events. In this scenario, a small group of stars forms first, and then gradually captures additional stars over time through gravitational interactions. This process can occur in dense star clusters, where stars are packed closely together and have frequent encounters. The captured stars may initially be in loosely bound orbits, but over time, gravitational interactions can tighten these orbits, eventually leading to the formation of a stable, compact system. This theory accounts for the age discrepancies we previously addressed, where stars in the same system have significantly different ages. Both of these theories face challenges in explaining all of the observed properties of undercuple star systems. The fragmentation theory struggles to explain the high degree of order and stability in these systems, while the capture theory has difficulty accounting for the formation of the initial group of stars. It is possible that a combination of both processes is at play, with fragmentation initiating the formation of the system and capture events adding additional stars over time. As we look to the location of these star systems, we discover an interesting trend. Exploring the metallicity variations, we find that stars within the same undercuple system often exhibit differences in their heavy element content, a phenomenon that offers clues about their distinct origins or accretion histories. Metallicity, in astronomical terms, refers to the abundance of elements heavier than hydrogen and helium in a star's composition. These variations suggest that not all stars in the system formed from the same homogeneous material or experienced identical evolutionary path. One possible explanation for metallicity variations is that the stars accreted material from different regions of the molecular cloud from which they formed. Molecular clouds are not uniform, they contain pockets of gas and dust with varying compositions. If different stars draw their material from these diverse pockets, they will inherit different metallicities. Another possibility is that some stars have undergone unique accretion histories, where they captured material from other stars or circumstellar disks, altering their original compositions. The implications of metallicity variations are significant for understanding stellar evolution in complex systems. Stars with higher metallicities tend to be more efficient at radiating energy, affecting their temperature, luminosity, and lifespan. These differences can also influence the formation of planets around these stars, as the metallicity of a star's protoplanetary disk plays a crucial role in planet formation processes. Scientists use spectroscopic data to determine the metallicity of stars. By analyzing the wavelengths of light emitted by a star, they can identify the elements present and measure their abundances. Charts showing metallicity levels across multiple stars in an undercouple system can reveal patterns and correlations that shed light on the system's formation and evolution. For example, if stars closer to the center of the system have higher metallicities than those on the outskirts, it might suggest that the central stars formed earlier and had access to more enriched material. Understanding metallicity variations in undercouple star systems requires detailed observations and sophisticated modeling. It is a complex puzzle, but by piecing together the clues, we can gain valuable insights into the origins and evolution of these fascinating celestial structures. From these insights, we can transition to our next discovery, which focuses on rare eclipsing events within these complex systems. Shifting our gaze now, we turn to the captivating phenomenon of rare eclipsing events within undercouple systems. These eclipses, where one star passes in front of another from our vantage point on Earth, are exceptionally unusual due to the complex orbital dynamics of these systems. The alignment required for an eclipse to occur is fleeting, making each event a treasure trove of scientific data. When an eclipse does happen, it provides invaluable information about the sizes, shapes, and orbital paths of the stars involved. By carefully measuring the changes in brightness during an eclipse, astronomers can precisely determine the radii of the stars and the inclination of their orbits. This data is critical for refining our models of these systems, allowing us to better understand the gravitational interactions and long-term stability. The rarity of these eclipsing events adds to their scientific importance. Each observation is a unique opportunity to test our theoretical predictions and improve our understanding of stellar astrophysics. Astronomers often use sophisticated computer simulations to model these systems, and eclipsing events provide a crucial reality check, helping to fine-tune the parameters and assumptions used in the models. Animations of eclipsing events in undercouple systems can help visualize the complex interactions that are taking place. These animations illustrate how the stars move relative to each other, highlighting the changes in brightness as one star passes in front of another. By studying these animations, scientists can gain a deeper understanding of the underlying physics and dynamics of these systems. These rare eclipsing events offer a glimpse into the intricate mechanics of undercouple star systems, underscoring the importance of continued observation and analysis. With these stellar shadows in mind, our investigation now turns to the potential role of dark matter within these complex stellar arrangements. Venturing into more speculative territory, we now consider the potential influence of dark matter on the formation and stability of undercouple star systems. Dark matter, an invisible substance that makes up a significant portion of the universe's mass, has long been theorized to play a role in the structure and evolution of galaxies. Could it also have a hand in the formation of these complex stellar systems? The idea that dark matter might influence stellar formation is still largely theoretical, but some models propose that concentrations of dark matter could act as gravitational seeds, attracting ordinary matter and triggering the collapse of molecular clouds. In regions where dark matter is particularly dense, such as the cores of galaxies or globular clusters, it's conceivable that these dark matter clumps could help initiate the formation of star systems, including undercouple ones. Another possibility is that dark matter halos surrounding these systems could provide an additional source of gravitational stability. Undercouple star systems are inherently unstable due to the complex interactions of so many stars in close proximity. The gravitational pull of a dark matter halo could help counteract these disruptive forces, preventing the system from flying apart over time. It's important to emphasize that these ideas are highly speculative and remain at the forefront of theoretical astrophysics. There is no direct observational evidence linking dark matter to undercouple star systems, and the models are based on simulations and mathematical calculations. However, the potential role of dark matter in shaping the cosmos is a topic of intense research. and exploring its possible influence on these exotic star systems is a natural extension of that investigation. While we are navigating the speculative edge of astrophysics, let's pivot to a more observable yet equally puzzling phenomenon: the scarcity of brown dwarfs within undercouple systems. Now, turning our attention to another intriguing aspect, we explore the notable absence of brown dwarfs in undercouple systems. Brown dwarfs, often called failed stars, are celestial objects that fall in between the size of a giant planet and a small star. They lack the mass needed to sustain stable nuclear fusion, setting them apart from regular stars. In the crowded environments of undercouple star systems, their scarcity presents a puzzle. One potential explanation for this lack of brown dwarfs is the phenomenon of ejection. In such a densely packed system, gravitational interactions are frequent and intense. Brown dwarfs, being less massive than their stellar counterparts, are more susceptible to being flung out of the system altogether. These ejections occur when a brown dwarf gets too close to one or more stars, gaining enough kinetic energy from the encounter to escape the system's gravitational pull. Another factor that might contribute to the paucity of brown dwarfs is tidal disruption. The strong gravitational forces exerted by multiple stars can wreak havoc on the delicate structure of a brown dwarf. Tidal forces can stretch and distort the brown dwarf, potentially even tearing it apart if it ventures too close to a massive star. This tidal disruption would effectively destroy the brown dwarf, removing it from the system. The implications of this brown dwarf deficiency are significant for our understanding of star formation and the survival of substellar objects in extreme environments. It suggests that the conditions within undercouple systems are particularly inhospitable to brown dwarfs, either preventing their formation in the first place or leading to their rapid destruction. This contrasts with other star-forming regions where brown dwarfs are relatively common. For a scale comparison, imagine a brown dwarf as the size of Jupiter, while the stars around it are the size of our Sun or even larger. The gravitational dynamics in these systems significantly hinder the presence and stability of such smaller objects. Understanding why brown dwarfs are scarce in undercouple systems sheds light on the complex interplay of gravity, stellar dynamics, and the formation of substellar objects in the most extreme stellar environments, which leads us to our next point: the impact these complex systems have on the potential for habitable zones. The 17th discovery involves the impact on habitable zones. Shifting our focus to the prospect of life, an intriguing question arises: can planets exist within undercouple star systems, and if so, can they sustain conditions suitable for life? The habitable zone, often called the Goldilocks zone, is the region around a star where temperatures are just right for liquid water to exist on a planet's surface, a crucial ingredient for life as we know it. However, in undercouple systems, the presence of multiple stars creates complex gravitational fields that significantly affect the potential for stable habitable zones. The challenge for any planet in these systems is to maintain a stable orbit. The gravitational forces from multiple stars tug and pull in various directions, making it difficult for a planet to settle into a predictable path. These forces can cause significant variations in a planet's orbit, leading to extreme changes in its distance from the stars and, consequently, drastic temperature fluctuations. A planet might swing too close to a star, becoming scorching hot, or drift too far away, freezing over. Moreover, even if a planet manages to maintain a somewhat stable orbit, its climate could still be highly unstable. The combined light and heat from multiple stars can vary in unpredictable ways, leading to dramatic shifts in atmospheric conditions. Such variations would make it challenging for life to evolve or survive, as consistent and stable conditions are generally required for biological processes to thrive. Consider, for instance, a diagram illustrating unstable habitable zones. In a single star system, the habitable zone is a relatively simple, continuous band around the star. But in an undercouple system, this zone becomes fragmented and chaotic, with multiple small regions of habitability that shift and change over time, which leads into our next discovery, which will be about the observation of unusually powerful stellar flares from stars in some undercouple systems. The 18th discovery involves unusual stellar flares. Beyond the challenges of stable orbits and consistent climate, planets in undercouple star systems face another significant threat: unusually powerful stellar flares. Stellar flares are sudden releases of energy from a star's surface, resulting in bursts of electromagnetic radiation, including X-rays and ultraviolet light. While our Sun occasionally produces flares, the stars in undercouple systems sometimes exhibit flares that are far more intense and frequent. These flares are potentially triggered by the complex magnetic interactions between stars in close proximity. The magnetic fields of these stars can become tangled and stressed, leading to sudden releases of energy in the form of flares. The impact of these flares on any orbiting planets could be devastating. Intense radiation can strip away planetary atmospheres, boil off surface water, and even sterilize the surface, making it uninhabitable. Moreover, frequent flares can cause significant climate disruptions, leading to extreme temperature swings and making it difficult for life to adapt. Even if a planet were to somehow develop life, these flares pose a constant threat capable of causing mass extinction events. To illustrate, imagine animations of stellar flares erupting from stars in an undercouple system, showcasing the intense radiation sweeping across the surrounding space and the potential impact on any nearby planets. Turning our attention to another effect of multiple stars, the next section covers tidal locking effects. Discovery 19 focuses on tidal locking effects. In the tightly packed environment of undercouple star systems, stars can experience significant tidal forces. These forces, similar to those between the Earth and Moon, can cause stars in close orbits to become tidally locked. Tidal locking occurs when the rotational period of a star matches its orbital period around another star. As a result, one side of the tidally locked star always faces its companion, while the other side remains perpetually turned away. This phenomenon has profound consequences for stellar activity and heat distribution. The side of the star facing its companion experiences intense gravitational tugging, which can lead to increased tidal stresses and enhanced magnetic activity. These stresses can generate stronger magnetic fields and more frequent stellar flares on the side facing the companion. Conversely, the far side of the star, shielded from the direct gravitational influence of its companion, may exhibit different magnetic properties and lower levels of activity. The heat distribution on a tidally locked star is also highly uneven. The near side, constantly exposed to the radiation from its companion, tends to be much hotter than the far side. This temperature difference can create significant thermal stresses within the star, affecting its internal dynamics and potentially influencing its evolution. Imagine a diagram of two stars in a close binary system, one of which is tidally locked. The diagram illustrates how one side of the locked star is always oriented towards its companion, while the opposite side remains perpetually hidden. Temperature variations across the surface of the locked star are shown, with the near side glowing intensely and the far side appearing cooler. The unusual effects of close proximity can also result in mergers, as we'll explore in the next section. Moving onward, Discovery 20 delves into stellar mergers. Stellar collisions and mergers are dramatic events that can occur in the crowded environments of undercouple star systems. The close proximity of stars, combined with the gravitational interactions among them, increases the likelihood of these violent encounters. When two stars collide, they can merge to form a single, more massive star. The process of stellar merging is complex and depends on various factors, including the masses, velocities, and trajectories of the colliding stars. Head-on collisions result in a rapid merging process, while glancing blows can lead to a more prolonged and chaotic interaction. During a merger, the kinetic energy of the colliding stars is converted into thermal energy, causing a significant increase in temperature. The merged star can become highly luminous and experience significant changes in its internal structure. One potential outcome of stellar mergers is the formation of blue straggler stars. These stars appear younger and hotter than other stars in their vicinity, defying the expected stellar evolution patterns. Blue stragglers are thought to form when two lower mass stars merge, creating a more massive star that reignites hydrogen fusion and extends its lifespan. Stellar mergers can also lead to the formation of rapidly rotating stars. The merged star inherits the angular momentum of the colliding stars, resulting in an increased rotational speed. Rapidly rotating stars can exhibit unusual magnetic activity and may even develop circumstellar disks. The impact of stellar mergers on the overall system can be significant. Mergers can alter the gravitational balance of the system, potentially destabilizing orbits and leading to the ejection of stars. The heavy elements synthesized during the merger can also enrich the surrounding interstellar medium, influencing the composition of future generations of stars. Envision an animation depicting two stars on a collision course within an undercouple star system. As the stars approach each other, their gravitational forces distort their shapes. Upon colliding, a burst of energy is released, and the stars merge into a single, rapidly rotating star. The merged star emits intense radiation and gradually settles into a new equilibrium state. Before the balance is fully restored, Discovery 21 examines the variations in rotation rates. Now, turning our attention to Discovery 21, we explore variations in rotation rates. Within undercouple systems, stars exhibit a wide range of rotational speeds, a telltale sign of their varied angular momentum histories. Unlike single stars that often have predictable rotation rates based on their age and mass, stars in these complex systems are subject to a multitude of factors that influence their spin. One primary factor is the initial angular momentum of the gas cloud from which the star formed. Stars born from regions with higher angular momentum tend to rotate faster. However, in undercouple systems, this initial condition is just the starting point. Gravitational interactions among the stars can significantly alter their rotation rates over time. Close encounters can transfer angular momentum from one star to another, either speeding up or slowing down their rotation. Tidal forces, especially in close binary pairs within the system, can also play a crucial role. These forces tend to synchronize the rotation of the stars with their orbital period, a process known as tidal locking. Another factor influencing stellar rotation is mass loss. As stars age, they shed mass through stellar winds. This mass loss can carry away angular momentum, causing the star to spin down. The rate of mass loss can vary depending on the star's mass, composition, and magnetic activity. The presence of circumstellar disks can also affect stellar rotation. These disks can exert a drag force on the star, slowing its rotation. Conversely, accretion of material from the disk can spin up the star. Magnetic fields also play a critical role as they can create a link between the star's interior and exterior, influencing how angular momentum is transported throughout the star. Consider charts comparing the rotation rates of stars in several undercouple systems. These charts reveal a wide range of rotational velocities, from slow rotators to rapid spinners, even among stars with similar masses and ages. This diversity highlights the complex interplay of factors at play. The implications of these varying rotation rates are significant, such as they can affect stellar activity, magnetic field generation, and even the star's ultimate fate. As these stars whirl at different speeds, the next discovery uncovers how the influence of galactic tides impact these celestial families. As we shift from the dance of stellar spins, let's now consider the grander stage upon which these undercouple systems reside and talk about Discovery 22, the influence of galactic tides. External gravitational forces exerted by the galaxy can indeed have a profound impact on the long-term stability of these intricate star systems. These galactic tides, generated by the overall mass distribution of the galaxy, can tug on the outer reaches of undercuple systems, disrupting the delicate balance within. Imagine the galaxy as a vast cosmic ocean, and these star systems as small boats sailing upon it. The gravitational pull of the galactic center and other large structures within the galaxy create tidal forces that stretch and distort these systems over immense timescales. For undercuple systems, which are already teetering on the edge of gravitational chaos, these external forces can be the tipping point. Simulations play a crucial role in understanding these effects. Scientists use complex computer models to simulate the motion of stars within undercuple systems over billions of years, while also accounting for the gravitational influence of the galaxy. These simulations reveal that galactic tides can gradually strip away stars from the outer regions of the system, reducing its size and complexity. In some cases, the entire system can be disrupted, scattering its members into the galactic wilderness. Animations of these simulations vividly illustrate how tidal forces reshape undercuple systems. Stars initially in stable orbits can be nudged into more eccentric paths, leading to close encounters and eventual ejection. The visual representation shows how a once tightly bound cluster can slowly unravel under the relentless pull of the galaxy. The strength of these tidal effects depends on several factors, including the system's location within the galaxy, its orientation, and its mass. Systems located closer to the galactic center or in regions with higher stellar density experience stronger tidal forces than those in the galactic suburbs. As the galaxy exerts its tidal influence, our next discovery examines the system's orientation. Transitioning our view, Discovery 23 invites us to consider the system's orientation. The overall spatial arrangement of stars within these systems reveals intriguing patterns or sometimes a distinct lack thereof. Unlike many binary or triple star systems, where stellar orbits often align within a single plane, undercuple systems can exhibit a more chaotic configuration. In some cases, the stars may appear to orbit in a somewhat flattened structure, resembling a distorted disk. But in others, their orbits are tilted at various angles, creating a more three-dimensional, almost spherical arrangement. This diversity in orientation raises fascinating questions about the system's formation and evolution. Several factors could influence these spatial configurations. One possibility involves the magnetic fields present during the system's birth. If the initial molecular cloud from which the stars formed possessed a strong, organized magnetic field, it could have influenced the alignment of stellar spins and orbital planes. Alternatively, the direction of rotation of the initial molecular cloud might play a crucial role. If the cloud had a well-defined spin axis, the resulting stars might tend to orbit in a plane perpendicular to that axis, though subsequent interactions could disrupt this initial alignment. 3D models help us visualize these complex orientations. By creating detailed computer simulations, scientists can reconstruct the possible formation scenarios and track the evolution of these systems over millions of years. These models often reveal that the initial conditions, such as the cloud's density distribution and angular momentum, have a significant impact on the final spatial arrangement of stars. The orientation of stars within undercuple systems isn't just a matter of aesthetics. It provides valuable clues about the physical processes that shaped these cosmic marvels. As we continue our cosmic exploration, the prevalence of these systems will be our next area of focus. Shifting our focus now, Discovery 24 shines a light on the common locations of these stellar marvels, globular clusters. Undercuple star systems aren't scattered randomly across the galaxy. Instead, they show a marked preference for residing within globular clusters. These clusters are ancient, densely packed spheres of stars huddled together in the galactic halo. The sheer number of stars within a globular cluster is staggering, often numbering in the hundreds of thousands or even millions. The high stellar density within globular clusters creates a unique environment that fosters the formation and survival of undercouple systems. In these crowded stellar metropolises, stars are much closer together than in the more sparsely populated regions of the galaxy. This proximity increases the likelihood of gravitational interactions and capture events, processes that are essential for assembling such complex multiple star systems. Imagine a cosmic dance floor where stars waltz and twirl, occasionally pairing off and forming new partnerships. In the dense environment of a globular cluster, these stellar encounters are far more frequent, leading to the creation of exotic systems like our undercouple stars. The gravitational forces exerted by neighboring stars can also help stabilize these systems over long periods, preventing them from falling apart due to internal chaos. Globular clusters act like stellar nurseries and retirement homes, providing both the ingredients and the stability needed for undercouple systems to thrive. Pictures of different globular clusters reveal the stunning beauty and complexity of these cosmic structures. From the sparkling brilliance of Messier 13 to the intricate patterns of Omega Centauri, each cluster offers a unique glimpse into the stellar processes at play. These images showcase the incredible density of stars, hinting at the dynamic interactions occurring within these crowded environments. The prevalence of undercouple systems in globular clusters highlights the importance of environmental factors in shaping the architecture of star systems. It suggests that these systems aren't just rare flukes, but rather a natural consequence of the conditions found in these ancient stellar swarms. As we continue our exploration, the potential of these systems being gravitational wave sources will be our next topic. Now turning our attention to a cutting-edge area of research, Discovery 25 explores the potential role of undercouple star systems as sources of gravitational waves. Gravitational waves, ripples in the fabric of space-time, were famously predicted by Albert Einstein and directly detected for the first time in 2015. These waves are generated by accelerating massive objects, such as black holes or neutron stars orbiting each other. Compact undercouple systems, with their tightly packed stars and complex gravitational interactions, could potentially be sources of detectable gravitational waves. The constantly changing gravitational fields within these systems, as stars orbit and interact, could generate these ripples in space-time. Imagine the stars in an undercouple system as dancers, their movements creating vibrations that spread outwards like ripples in a pond. However, it's important to note that this field is still largely theoretical. Detecting gravitational waves from undercouple systems is incredibly challenging, requiring extremely sensitive instruments and sophisticated data analysis techniques. The gravitational waves produced by these systems are likely to be relatively weak and buried amidst the noise of other cosmic events. Despite the challenges, the potential implications for physics research are very interesting. If we could detect and study gravitational waves from undercouple systems, we could gain valuable insights into the dynamics of these complex environments. We could also test our understanding of gravity in extreme conditions and refine our models of stellar evolution. Visuals can help illustrate the concept of gravitational waves and how they might be generated by undercouple systems. Animations can show the stars orbiting each other, creating ripples in space-time that propagate outwards. Diagrams can illustrate the different types of gravitational waves that could be produced depending on the configuration and dynamics of the system. With so much to learn, let's summarize our stellar journey of strange facts. As our cosmic journey draws to a close, let's recap the 25 strange discoveries about undercouple star systems that we've uncovered together. From the unstable orbits of stars to the surprising variations in chemical composition, these systems present a unique puzzle to astronomers. We've explored the age discrepancies within these systems, the unexpected presence of circumstellar disks defying gravitational forces, and the unusual light curve patterns that challenge our existing stellar models. We've delved into the high stellar density, the puzzling absence of massive stars, and the evidence of stars being ejected from these dynamic environments. We also highlighted the X-ray emission anomalies and the surprising alignment of stellar spins, pointing towards unknown formation mechanisms. The disruptive forces on protoplanetary disks and the paradox of their very formation have showcased the complexity inherent in these systems. The metallicity variations have suggested diverse origins, while rare eclipsing events have offered invaluable data. We've also touched on speculative ideas such as the potential role of dark matter and observed the lack of brown dwarfs impacting our understanding of star formation and survival. We considered how these complex gravitational fields impact habitable zones and the powerful stellar flares these stars unleash. We've seen tidal locking effects and stellar collisions and the variations in stellar rotation rates. The influence of galactic tides on the stability of these systems, along with their unique spatial orientations and prevalence in globular clusters, adds further layers to their mysteries. Finally, we pondered their potential as sources of gravitational waves, opening up new avenues for physics research. These undercouple star systems not only challenge our understanding of stellar dynamics and formation, but also beckon us to reconsider the very laws that govern these cosmic arrangements. As we look out into the cosmos, it's clear that the universe continues to hold secrets that inspire awe and encourage further exploration. Now, I invite you to ponder these mysteries, share your thoughts in the comments below, and suggest future topics for us to explore. If you enjoyed this cosmic journey, don't forget to like this video, subscribe to our channel, and hit the notification bell for more space explorations. Together, let's continue to unravel the enigmas of the universe, one star system at a time.